In this lecture, we're going to talk about the introduction to soil stress states, Mohr circle, and combined stresses. And in engineering, we deal with two things with materials. One are the way they deflect, and the other one is the way that they are stressed. And we're going to, soil mechanics is quite a bit of both. We've talked some about the way in which soils stress themselves. And we're going to start now to transition into a topic where what happens when we add stresses to them. What happens? And that, of course, gets us into the stress part up to failure stresses, and that includes that takes that into account, plus settlement. And we're going to talk about settlement in this course and in the next one. So let's talk about stresses first. Most engineers, traditionally, the way it's done, we worry more about stuff overstressing and failing as opposed to excessive settlement. That is not necessarily, in soil mechanics, we're more interested, catastrophic failure is a serious problem, but it's not, the settlement is generally speaking what gets us more often than not in geotechnical problems. And that's a theme you're going to hear me go over and over and over and over and over again in this course and the next one. So let's begin talking about stresses though, because the two are not unrelated. Like any other engineering material, experience stresses. We've already looked at stresses due to the self-weight of the soil and the water combined, effective stresses, total stresses, pore water pressures, and that kind of thing. We talked about that. And we've also talked about stresses, what happens when the water has the bad taste to move, which it does very frequently. As we build structures around soils, both, we're going to talk about, we talk about foundations and earth structures and lateral earth pressures, both on top and next to soils. And we're going to hit both of those in this course. The stress states will change. And that change can have any number of results. And we're going to talk about what those results might be and how you manage those results. We use three basic concepts in the way we look at stresses. And I'm going to try to, and soil mechanics has a nasty habit of putting these in front of students without really explaining how they how they actually interact with each other and why they interact. And I'm going to try to see if I can sort that out, because that's something that took me a long time to actually figure out. One of them, elastic deformation stress, the non-path dependent. I'm going to talk about path dependence, which is like most other engineering materials. Now, just don't spread this around, but what really with soils, there ain't no such thing as real elasticity. In rocks, you see it. Soils, not so much. There's not really, we can see practical elasticity, and we're going to talk about practical elasticity, but real elasticity, And it's not the only engineering material that experiences that problem. Cast iron is the same way, for example. It does not have real elasticity, and there are other materials that don't have real elasticity. Then there's plastic deformation or path-dependent deformation, which can be catastrophic under certain conditions. I'm going to talk about how that works. And last but not least, we have consolidation settlement, which is a volume change during the soil particles rearranging. We talk about how the particles rearrange and the fact that their void ratios are different and can change for a set. We talked back when we talk about relative density, we talk about the fact that the void ratio will change, and a lot of other things change too. It makes sense that soils are different if you rearrange and either loosen the particles or compact the particles. And that's certainly the case. We're going to talk about how that works too. So those are the three things we break down. We're going to talk about the first two. In this lecture, we're going to deal with the first two. The consolidation part comes just a little bit down the road. Soil stresses can be analyzed with methods used elsewhere in mechanics and materials. In fact, some of these methods actually were more developed with soil mechanics in mind than they were with normal component types of things that you're familiar with up to now. There are two important differences that you may have between soils and regular engineering materials. Engineering materials are generally things that we take and we process these in some fashion and get a material whose properties are reasonably predictable. Soils aren't that way to start with. They're materials in nature. They've been the result of many years of their own stress and particle rearrangement and whatnot, and depositions and whatnot, and therefore, because their formation is complex, their engineering properties can be very complex. The two things is, and one I've just mentioned, one of them is soils deform plastically almost exclusively. There's very little such thing as a true elastic deformation of soil. So rocks are a little different, but with soils, not so much. The other thing, and that's one thing that throws students up, because most early mechanics of materials education focuses on elasticity, and justifiably so. There are good reasons to do that. The other one is they act in a 2- or 3-dimensional continuum. Traditionally, particularly in civil, we have beams, we have axial elements, spars. I'm using a fine element term, my apologies. But we have spars, we have beams, we have elements, and they generally, either the stress acts in one direction, basically. In soil mechanics, we're dealing with what we call a semi-infinite medium, and it acts in 3 directions. Actually, we can simplify many problems to a 2-dimensional type of thing. And that is something which is called continuum mechanics. Continuum mechanics can be, particularly with material that is as non-elastic as soils are, that can be a little tricky. Soil mechanics, that's where the experience factor comes in with soil mechanics. But we have some tools at our disposal, and one of them is Mohr circle, which is something you should have been exposed to in mechanics and materials. It's a convenient way to show the relationship of stresses, normal and shear at a point. At one time, the graphic solution was the best way to handle the algebra, but this has been superseded. However, word to the wise. If you are proficient in CAD, you should be. As an engineering student, I know I bellyached many years about the fact that CAD was not required at our institution. It is now. You can actually get exact results by using Mohr circle in CAD. In fact, graphical methods which were used for approximate solutions can be done exactly now in CAD, although a little tricky, a little different. One important thing to remember about Mohr circle, because of the way it's taught and because of the way engineering is taught, we traditionally think of Mohr circle in terms of theory of elasticity. It is not. Mohr circle, let me show you. Mohr circle is this little square we have here. Actually, it's a cube, but let's just kind of lay aside the 3 dimensions. Let's get on 2 dimensions. It's a little easier to understand. This little square has stresses here, and normal stresses here, and normal stresses here, and it also has shear stresses as well. We're talking about those. But if it is not moving, in other words, static equilibrium applies here. You take a little square or a little element in the soil. Every one of those, if it's not moving, has to be in static equilibrium. It doesn't matter if the deformation is elastic. It doesn't matter if it's plastic or whatever. It has to, in order for it to be a continuum, unless it's ripped apart, and we're talking about that, as long as it's together, it's got to be in static equilibrium. And that's not only independent of the state of elasticity of the piece, it's also independent of the direction. For example, the thing in the soil doesn't understand the fact that you have put a coordinate system on it. That's a problem for many students, because many students, when they're first learning statics and they're first, get fixated on their coordinate system. Coordinate system is, strictly speaking, arbitrary. And you can actually manipulate coordinate systems to produce results which are more convenient. And we're going to talk about how to do that with this, definitely applies. But the fact of the matter is, if the coordinate system is this way and this way, and someone comes along and rotates the coordinate system, it's this way and this way, the static equilibrium holds. As a result, no matter what coordinate system you pick, the element is still in static equilibrium. You cannot change that. So that's an important thing to remember about Mohr circle. It does apply in not only elastic but plastic, as long as you have a continuum. Mohr circle in 2 dimensions has been defined. You've probably seen these equations before. If you pick an XY coordinate system, or traditionally in geotech we have an X this way positive and a Z downward positive. You're going to see both in this. And Mohr circle requires that if you have X and Y, and then there's shear stresses there too, by the way. And so we have these nice equations here that show, if I have these 3 right here, the X, Y is in terms of the principal stresses. Now, what in the world are principal stresses? Principal stresses are if you keep rotating it, and I'll talk about the convenient axis. We're going to talk about if you rotate an axis, there's 2 points which are important. I won't keep, as long as I keep rotating this thing, even though static equilibrium does not change, the values of the 2 normal stresses and the shear stresses will change. And there are 2 angles at which we are of special interest. The first one, and probably the most important, are called the principal axes. The principal axis, you can actually rotate this thing to the point where there are no shear stresses. At some axis, there are no shear stresses at all, and you have a sigma 1 and a sigma 3. And ways why we do 1 and 3 is a result of more Coulomb failure theory, and we're going to talk about that, but I'm not going to go into that. Just let it run. And at this point, you've got, if I know for any coordinates set up sigma x, sigma y, and tau xy, I can compute the 2 principal stresses. I can also compute, using some other equations, the orientation of that. The second, which is the axis of maximum shear stress. There is also an axis at which point you have the 2 normal stresses are equal and the shear stress is at its maximum. That is the point of maximum shear stress. Both of these are important, and they are related to each other, certainly are. And we're going to talk about that because we use one or both of them to determine the state that at what point how likely this little element is to fail. Let's take an example. This is an example of an embankment. An embankment basically where it goes infinitely this way. It comes up to a point and then it slopes down. Something you see quite a bit in transportation. And we're going to talk about the stability of that slope and whatnot towards the end of the course. In the meanwhile, we're going to talk about the stresses of that. If I start with a level ground and I add that as an embankment, I'm going to induce some fairly complicated stresses. And this is a problem which your Soils and Foundations manual talks about briefly, and I don't get too much into that because introduction to that gets to a theory of elasticity problem, one of the most celebrated ones in soil mechanics. But anyway, we're talking about 3 points. The point A here, which is under the infinite part, or the flat part of the infinite part of the embankment. Point B, which is kind of halfway between the two sides of the slope, and point C, which is way out here. Now, these stress lines are to show you different, in the weather we'd call them isobars, and that's not a bad thing because common stress. The pressure is the same. The big difference is that since for fluid statics, we don't have shear stresses. But we have shear stresses and we have normal stress, and they vary under this embankment. Towards this way, you're going to get, if you keep going, you're going to get to the point where the shear stresses kind of die out. You get normal stress like that, and then, whatever reaction you get due to Poisson's ratio this way, you live happily ever after. Over here, you get to the point where the embankment has no effect at all. In the middle, it's different. So let's look at those 3 points. My primary purpose is not to get into embankment loading as much as it is. The first, now, P is, generally speaking, this is important because inevitably, sooner or later, you're going to have a surcharge problem. Might as well go ahead and stop and let's talk about surcharge problems. We're going to talk about loads induced by square structures on soils, rectangular structures on soils, and we're going to talk about circular structures on soils. But one of the things we're also going to talk about, and these loads can be due to the weight of the concrete, for example, most of the time it's concrete. The weight of the slab is part of the load. What we put on top of it, the floor loading. If we've got a multi-story building, we've got multi-loads. So those are the load. But another type of loading, which we call surcharge loading, is usually refers to when we put a lot of additional soil on top of this. Now, you see here we've got a nice uniform level surface minding its own business. When we roll in here and do the excavation and fill and gray work we talked about the last time, we put soil here and then it slopes down like this. In this particular case, we've shaped it nice so it slopes. But on this end of it, assuming that the water table doesn't get into this, or at least, the water table is still down here somewhere. The pressure that this surcharge exerts in this area on the ground is equal to the unit weight of the surcharge times its depth. And that's why and that's a surcharge load. Now, in this particular case, everything and all things come to an end. this comes to an end and then it slopes down. It could just, if we really, if it were cohesive enough, we could, do a nice cut this way, and we're going to talk about that. But when it comes down, it slopes down, and the loading under it is complicated, as you see. So, but we have a little concept in soil mechanics called the uniform surcharge. And to be honest, it is one of the simplest concepts in soil mechanics. But it is also one that students absolutely go bananas over. Let's say that go infinity this way. Let's say that we could go infinity both directions. Let's say that this surcharge is so large that these end effects, like we see here, disappear. And I'm kind of getting ahead of myself, but I want to nail this point home because I know this will be a problem. Say this way and this way. So let's say then that both directions. If it's infinite in both directions, it is referred to as a uniform surcharge. If that happens, or if I tell you that happens, then what you assume is that this soil starts out with a zero stress here, with effective stress as they increase in the normal fashion. If I tell you a uniform surcharge is on top of this, there's two ways I can tell you that. One of them is to say, well, we have, for example, just out of the blue, a surcharge which has a unit weight of, say, 18 kilonewtons per cubic meter and a height of 2 meters. That means that 18 kilonewtons per cubic meter times 2 means that uniform surcharge exerts an additional stress of 36 kPa over the entire soil area. And it doesn't have all these funny end effects or side effects. In other words, the whole thing increases. That's the effect of uniform surcharge. So with that out of the way, let me proceed to the example. We have 3 points. Now, I went off on that. I'm getting ahead of myself. I know it. One of the advantages of video is that when you're I had the bad habit in class. I had a lot of bad habits in class. I have a lot of bad habits though. One of them is to just mention stuff in passing, and the students, some are paying attention, some are not. Some are not there for whatever reason. They get to the test, and that mention in passing suddenly becomes part of their test. One of the advantages of video is that you can go back and actually see those mentions more than once. And that's good. That's a good thing. That's one of the advantages of video lecturing. There are disadvantages, as my students remind me of, but that's one of the big ones. Okay, with that out of the way, I set this up, you remember the example I gave back here where I said, 2 meters, 18 kilonewtons per cubic meters, 36 kPa. That is the uniform surcharge load, and obviously that doesn't apply across the whole thing. But what it is, though, is the baseline P. In other words, the P that's mentioned here is in fact the surcharge in the uniform area. Even though, because of the fact that it's not infinite or semi-infinite or whatever, doesn't apply. But P is, but the first one over here what's over on the left side is really very heavily loaded. You can see that. The sigma Z is 0.9 P. That means it's almost a uniform surcharge this way. And then we have 0.77 P this way. And that's mostly due to lateral loading and Poisson's ratio loading. And we're going to leave that. It just is. It's something you understand. We're going to quantify that when we get to lateral earth pressures. And then we have these small shear stresses, 0.6p and whatnot. That's a nice stress state. If I were to rotate that 12 degrees this way, what I will end up with is the principal axes, which mean that the sigma 1 is 0.99p. It's almost it's almost uniform surcharge state. And the sigma 3, they use, this came from NAFAC TM7, they use Roman numerals for whatever reason, is 0.76. Not much different, but some. And then this is how they draw it out on a Mohr circle, this way. And notice that for every theta that the little element actually rotates, it's 2 theta on Mohr circle. You get the Mohr circle point. This point and this point are the stress states up here, and this point and this point are the stress states there. So therefore, there's not much difference. This is fairly close to the principal stress, so there's not much difference. That's state. That's the first state. Now we're going to pick one in the middle. Now this is interesting because I mentioned to you a few minutes back about the stress state, the orientation at which you have maximum shear. This is it right here, people. You'll notice that the two normal stresses, 0.5, are equal. They're the same. And that this shear stress right here is 0.25p. And that's actually, that all follows. What this means is that the stress states here are here and here on Mohr circle. And then when we rotate this 45 degrees, we go 90 degrees to the principal axis, and the principal axis is at 0.72 and 0.28. These are the principal axes are here and there. And you can and should apply these equations to that, and to make sure I'm not just blowing smoke in your face. Now, word to the wise. You know, one of the joys we have now is the use of spreadsheets. And one of the joys of using the spreadsheets is that if you can set up a spreadsheet to do a calculation and you change the numbers, as long as the conditions under which you change it works, you can change the you can actually get the same result. So one way you can use this type of thing is to calibrate your spreadsheet for these results. Because if you take these values and you put them into these equations, you should get the same principal stress. They're actually a little bit off because this was done in the slide rule era. The last one is it very lightly. Over here, the normal stress is actually, the horizontal stresses are actually greater than the vertical normal stresses. The shear stresses are substantial enough, but not really, because they're, again, if you plot these on Mohr circles, this stress state goes here and here. And by the way, it doesn't make any difference which one you plot first, whether you plot them, however. And this stress state, which is off of here, 12 degrees again, like it was here, is there, and there. Sigma 1, sigma 3. So you have the same thing. It's kind of the mirror image of this one, which kind of what you'd expect. And again, it's that these problems are examples of how Mohr circle works in actual soil mechanics. Now, because I would suggest you go through these and use these as examples. So how in the world do we use the two-dimensional stress concepts in three-dimensional soil space? And that's a challenging issue. Again, we talked about when we were in permeability about for example, the flow per unit length, per meter or kilometer or whatever we had. And in stress, it's kind of similar. There are basically three, and I use some fairly primitive looking graphics. You can see a lot fancier stuff generated now. The first one, and the one that we see, in particularly in elementary mechanics of materials, is so-called plane stress. And basically we assume that all the stresses are in the plane and that there are no stresses this way. In other words, in the z-axis, or stresses are zero. That's good for, test coupons and relatively thin elements. For soil mechanics, we don't see that many plane stress problems. The second is the plane strain problem, where basically we say, yeah, we have three-dimensional, we have X, Y, and Z stresses, but there's no strain in this direction. In other words, there's no change in volume in that direction, and that really impacts the way we apply theory of elasticity to it. And last but not least, we have an axisymmetric case, where we basically take this and we wrap it around the axis. We basically use that as sort of a plane strain wrapped around a pole kind of thing. Those are the three. Most of what we're going to deal with soil mechanics is plane strain or axisymmetric. Axisymmetric is very handy for certain types, particularly when you get into deep foundations. You'll see a lot of axisymmetric application. Let's make a few observations. We do not allow tension soils. In theory, with cohesive soils, we could have it. We don't. We're going to see why. Although principal stresses coincide with the ZY plane, in other words, you very frequently in geotech, the principal stresses, are the first principal axis is this way, and the third principal axis is this way. I said ZY plane. I said ZX. You see both notations in either X is ZX or ZY. It doesn't make any difference really, because both of those are perpendicular to the z-axis in an orthogonal coordinate system. And the last one, that's not always the case. We do that shorthand very frequently in soil mechanics, but it's not always, strictly speaking, the case. And the last one is the understanding of principal and shear stresses is critical in determining the bearing and frictional capacities of soils. I'm going to stop. I'm going to mention the fact that and I'm going to talk about how in the next semester how my strange PhD came into being. But for my PhD thesis, I developed from the ground up a finite element model of the soil with a driven pile in it. And I had to learn honestly, I had to learn a lot about continuum mechanics, practical continuum mechanics, and how it is coded into FE. That's a lesson that many engineers do not learn, and the fact that much of their education doesn't prepare them for that is unfortunate. So I'm going to try to see if I can fill in it. There are a few tricks I learned, and one of the most important is the stress invariance. There are more than one stress invariant, but I'm going to talk about one stress invariant. Stress invariance, I mentioned the fact that static equilibrium doesn't care about the coordinates. What that means is that there are some things that don't change no matter how, the static equilibrium doesn't change. There are other things mathematically that don't change. And one of those stress invariants. The only stress invariant we're going to talk about in this course is the first one. And the first stress invariant is really simple. The sum of the principal stresses is always equal to the sum of any of the two normal stresses at any orientation of the element, at any coordinate system. Therefore, and you can check this looking at the stuff previous to this. If you think I'm trying to blow smoke in your face, you can. Therefore, sigma 1 plus sigma 3 for a two-dimensional system is always equal to sigma x plus sigma y, which is a nice shortcut. It's also a nice check to make sure you haven't screwed up your math. And that's always a good thing to do. So that's first, that stress invariant is important to understand in terms of how all this works together. The rest of them are more arcane, and you can get that later on. Now let's talk about frictional forces. And I'm kind of sliding into failure theory at this point. The thing that separates, without going into a lot, I'm going to kind of approach this subject backwards from the way it's frequently done, because usually we talk about failure theories. We talk about, they talk about planes, about maximum stress and maximum strain and maximum shear stress and Mohr Coulomb and octahedral and all this stuff. That's the way it usually is discussed. Because I'm only going to really work on one theory in this course and the next, I'm going to try a little more intuitive approach. Let's start with frictional force. You remember from statics, if you put a block on a level surface, let's just leave the surface level, and you apply, and the weight of the block is usually the normal force. And I apply a tangential force. We know that the maximum shearing resistance force, which is shown here, is equal to the normal force times some coefficient of friction. Usually we call it mu, is what we normally do. And if we we keep increasing the tangential force until the point that we exceed the shearing resistance, then the block will move. And usually there's a breakaway with that, and it's a little bit once you to get started, but that's a different subject. And at the point where we get movement, basically the bond we have between the table or the flat surface and the block is broken. We have failure. And if we did a little math, we actually use a force triangle down here. We do a little math, and basically the normal force over the shearing, the maximum shearing resistance is equal to the tangent of some theta m. In other words, some angle. The ratio of those two. In fact, we have this little equation here, which is Fa. The tangential force is equal to the normal force at failure is equal to the normal force times the tangent of that angle, which we define here. We get that's a failure theory. Very simple one. If we, without going into the math that gets from point A to point B, if we apply this to soils, the shear stresses over the normal stresses are equal to the tangent of a theta, or actually we usually call it phi, which we'll deal with that later, or tau, the shear stress, is equal to the normal stress times the tangent of phi. In other words, the shearing stresses is equal to the normal stress times tangent of theta, or phi. The problem the thing that makes soils different is that is that they have is that for cohesive, for granular soils, this is pretty much the deal. However, some soils have cohesion, which would tend to kind of act like a very light glue, or maybe a light glue or sticky stuff on the surface. And that sticky stuff is actually a chemical bond, which we talked about in the beginning of the course. So what we do is we add a little C called the cohesion. And the critical shear stress is equal to C plus the sigma prime, which means it's usually the effective stress, times the tangent of theta, or more properly phi. And that is Mohr-Coulomb theory in a nutshell. So how do we apply this? Well, this is how we do it. And this is important, so pay attention. The frictional model suggests that the block is able to resist movement up to a point after which the movement is continuous with the applied force. That is referred to as a purely plastic model. In other words, nothing happens until you actually break the bond, at which point stuff happens. However, we don't, purely plastic models are used in soil mechanics in some situations. However, they're not common with soil mechanics. They're not, usually we have some deformation before we actually break the bond. Now that's very rough, because soils, as I said earlier, kind of don't do it this way. In other words, elastic and then to a point, and then either one way, one of these three ways, is an elastoplastic model. In other words, it deforms a little bit, and then all of a sudden it breaks. If there's no further increases for it, it's a purely plastic. If it actually, just you change the slope and tries to keep the fight going, it's a hardening model. And if it just, gets softer with, it just really goes down the drain, it is a softening model. But what we're going to do is we're going to assume, for purposes of this course and the next, we're going to assume Mohr-Coulomb failure with an elastic, purely plastic deformation model. Where we're going to assume that when we start stressing the soil, we do it elastically to a point, even though the soil actually does more like this. And the relationship between this and this is one of the nastiest topics in soil mechanics, but it's also an important one that's getting a lot more interest. It's called strain softening, and I'm not going to, that's a whole different field in and of itself. But it's an important one because a lot of what soils do can be explained by strain softening. But what we're going to say is that we're going to take a model that looks like this and we're going to replicate it look like this. And for many soil mechanics problems, even though that model is, as one colleague of mine in Europe would say, was just crude, it's worked pretty well. And attempts to develop other soil models have had mixed success. The failure criteria of soils is like this. If we take Mohr's circle, now we can have for, and this again, you see the Roman numerals for the principal stresses. If we have two principal stresses, it'll create a Mohr circle. And any stress around the circle is actually applied to it. Somewhere out there, if we get failure, we get to the point where, this circle is so big, basically, just to try to cut to the chase on, that somewhere in here it crosses the line. The soil crosses the line and experiences failure, at least at that point. If enough soil crosses the line, you have catastrophic failure, which we'll talk about when we get to slope stability and lateral earth pressures. But you get to the point where it's big enough. That big enough is defined by whether this circle crosses this line, which of course is defined by the Mohr-Coulomb failure. And traditionally we refer to this as the Mohr-Coulomb failure envelope, because not only can it be defined this way, it can be defined this way too. And that is the, if we get across that, then we have failure. And the shear stress at failure is equal to the stress state at which point this first touches this line. That's failure. And you see here defined by the Mohr-Coulomb stress. We're going to see how that works. Basically, as long as the Mohr-Coulomb circle, the stress is within the envelope, and it's better illustrated here, the stress is in a legal elastic state. When the circle touches the envelope, failure begins, and we define that as follows. In other words, we use this equation, which is derived from Mohr-Coulomb failure theory. If this stress state is all equal to 0, we've hit failure, and basically that says that this line is right there. And traditionally in solid mechanics, we emphasize that point. We fixate on it, really. That's how we determine if a stress state is subject to failure or not. If it hits that point, it's failed. The question is, that's kind of a hero or zero type of approach to it. It doesn't really help us. And when we get into finite element analysis, we need to know a lot more than that. So what we do is we develop a little thing called the failure function. Instead of always setting that expression, you notice these two expressions are basically the same except for what's on the right-hand side. In that case, F. Let's say I start here with a confining stress, sigma 3, is constant, which many cases, for example, the effective stress is constant. I start loading it with something. And I reach to the point, and as long as this circle is below here, this failure function will continue on in a negative way. In other words, the distance between the closest point here and that line, as long as it's negative, we're within we're within the failure envelope. When it hits 0, we've hit the failure on, and when it's positive, we are in a legal stress state. We have experienced failure. This is not a good thing. The failure function allows us to, instead of the hero or zero approach, the way this is traditionally taught, allows us to actually determine, actually get an idea of how close we are to failure. In finite element analysis, if you're using a Mohr-Coulomb failure model, this is the finite element program is constantly computing that failure function. It tells you not only how close, you might use a factor of safety with it. You might, that kind of thing. You might be able to have a factor of safety. You might, whatever. But in any case, you can use the failure function to find how close you are or if you're over the line. And usually we don't hand calculate those, but they could be useful if you want to put, say, a factor of safety on the failure function. By the way, I said diametral failure function. The reason why is because this, as I said, this envelope also goes down this way, even though a lot of times we don't draw that. And diametral means that it's this distance plus the distance, in both directions. In other words, this way and this way. Obviously, 0 is the same both ways. So, in other words, the point of failure doesn't care if it's diametral or radial, but the answer will be off by a factor of 2. Now I'm going to introduce another mnemonic aid for education called the PQ diagram. You'll notice that this can be a real kind of weird, because if you're trying, let's say if you know this y-intercept, this one says a y-intercept of 0, for example, This one, the cohesion is the y-intercept there, and this slope, which of course is the tangent of phi. By the way, phi, let me stop. Phi is the internal friction angle of the soil. The soils have their strength because the particles have friction against each other, not just against something else. They have friction with each other. And for purely cohesive soil, there is no strength in the soil if phi is 0 and C is 0, or, which is usually either, for any soil, you're either, if C and phi are both 0, the soil probably doesn't exist. You're going to get one or the other or both. But phi is the internal friction, and it's a measure, and we're going to come back to this, of how, soil, when particles rub together, they have friction. And you'll notice with the, in classic Mohr Coulomb phase theory, that the strength here is equal to sigma, the normal strength, times the tangent of phi. What that means is that unless there's some kind of external pressure on the soils, they have cohesionless soils have no shear strength at all, even if they have a positive phi, which they usually do. So keep that in mind. For a cohesionless soil, the strength is both due to its internal properties and the pressure, usually the effective stress, that is applied to the soil. But dealing with these circles and tangents can be a bear. Can we fix that? Yes, we can. And what we do is we use a PQ diagram. Now you ask, what is a PQ diagram? I have on my website, and it's probably the easiest way to explain it rather than going through on this video, what PQ diagrams are. But basically, this is how they work. Instead of, with a regular Mohr Coulomb diagram, you've got sigma this way and tau this way. With a PQ diagram, P is equal to the first principal stress plus the third principal stress over 2. And Q is equal to the first principal stress minus the third principal stress over 2. By the way, the first principal stress minus the third principal stress is the deviator stress. Just keep that. We're going to come back to all. I'm just introducing you the first time. And basically the advantage to that is that instead of having a lot of circles, for example, if I have multiple stress states of the same soil, I'm trying to figure out what the properties are, I could actually use that we would call the triaxial test. We'll come to that. I would have this here, and then this here, and then this here. Whereas if I have a if I have this, those circles are reduced to points. And it's a lot easier to draw a line through points than it is through to do it with circles, with tangent circles. Now you can do that, especially if you got more than 2 of them. If you have 3 of them, the chances there's no necessity for those to line up perfectly. And then if they don't, you can use least squares method to figure it out. In fact, word to the wise, if you want to find out what the phi, if you've got two specimens, and you want to find out what the phi and C is, you can use this because these reduce to points. And that makes the graphing. This is used in other applications in soil mechanics more frequent, but it's a good mnemonic aid. You're seeing it more often. But like I said, I would strongly suggest you look at I'm going to go over in brief what this is all about in this example problem. But to get the blow by blow, you really need to look at my website and the treatment I do on the subject of PQ diagrams. But let's get an example. Let's say The soil, the cohesion is 5 kPa. I'm going to talk more what that means later. And the phi is 30 degrees. Internal friction angle, 30 degrees. I have these two properties. With a more Coulomb soil, that defines the failure and everything, depending on what stress state. Find the failure line plots of both the sigma tau, which is this equation, which we've looked at, and the PQ diagram. And I go into in my website how to get from here to here. And again, P is equal to the two principal stresses, the sum of them divided by 2, and Q is the difference of them divided by 2. That incorporates the shear stress in them. However, you say, well, you didn't give us any principal stresses. You're right, I did. I surely did not. But what I am going to give you is this. I've already given you the tau sigma diagram and the failure envelope you get out of that. All you need to do, this is a typical y is equal to mx plus b type of construction. If I ask you to plot this, then this is y, this is b, the y-intercept, and this is m. The slope is tangent of phi, and x is this. Because, as you remember from those, if you go back, this is sigma and this is tau. It's just straight up, linear, straight up line. For a PQ diagram, and I actually show how the math works on getting from this to this, the Q, which is the Y, is equal to mx. Now, m is tangent of delta. X is P. The P-axis is this way, and the Q-axis is this way. And the y-intercept is c times the square root of 1 minus tangent delta squared. In order to do this properly, the way you do it, first of all, you have to transform the slope from phi to delta. And you do that by noting that tangent of phi is equal to tangent of delta is equal to is equal to sine of phi. So, if I know the sine of phi, which, by the way, 30 degrees is a half, then I take the arctangent of a half in this case, and I get tangent of delta, which happens to be 26.6 degrees, which is the easy part. And don't forget, if you're doing this in a spreadsheet, be advised that spreadsheets do their angles in radians. I've had all kinds of, never mind. Then that's first thing. That's you transform the slope. If you compute the delta, then you can tangent of delta and you got the slope. Then you transform the y-intercept by multiplying the cohesion, which you're given, by the square root of 1 minus tangent delta squared. And that, in a nutshell, is how you transform from tau sigma to PQ diagram. Once you get those two, you can result in the y-intercept, or the Q at P is equal to 0, of 4.33 kPa. And then you plot them, and you get something that looks like that. Again, you need to look at my online tutorial on PQ diagram. It's not that difficult. There are advantages to this, and I'm going to come back to this when we come back to when we get into other topics. One thing I'm going to mention is that for those of you who are sitting there thinking, he's in the trees, and you look online, nobody else fools with PQ diagrams. Since I posted that in 2018, it has become one of the most popular pages on my site. There's definitely interest in it. So it's not just something that we pull out of thin air. So with that concludes the first part, and it's kind of leaves everybody hanging, but it's not that bad really. I'm going to repeat myself on some of this stuff. We're going to come back to it. But in any event, in the meanwhile, thanks for watching, and God bless.